Hello everyone, welcome to MLAS 700, and this is the last lab of the semester, so yay, and last lab of the class. And what we're going to do is we're going to sprinkle in a machine learning model into this. It's going to be a very fast, lightweight model. It's going to be based on just pure math on this, and a linear regression that we're going to turn around and do a predictive output to the serial monitor based on based on the data that's being provided off of the analog voltage pin. So let's go ahead and see if there's what do we need to do to sprinkle into this to make that work. So basically we can take our code from what we built last time in our last lab. We're going to do the fast LED H, we're going to do the num leads num LEDs LEDs 8. This all stays the same, there's no change here. And then what we're going to do is we're going to create a linear regression model, and we're going to get that set up. These are adjustable. You can kind of sensitize them, but we're going to create a slope first. Because remember, linear regression is essentially y equals the mx plus b. That's what it is. So we're going to set the slope, and we're going to create an example slope of 1.6 as a starting point. And we can adjust these. Float intercept, so we have to do an intercept as well. 0.5, and then example intercept value. Okay, so that gets us going from a high level setup for our linear regression, and then we'll head on over to our setup here. And in our setup, this is we're going to still do the these two pieces here. I'm going to add in a brightness level. This is just something to fast LED set, that was it, set brightness, and then we're going to set it to 55 for right now. And you can set this value can range between 0 and 255. Okay, and that takes care of the void setup. So let's move over to the void loop. The voltage pin is the same. The float voltage value 1023 times 50, that's the same. But now what we're going to do is we're going to apply the linear regression. To predict the number of LEDs that are going to light up. Okay. And then we're going to do a float predicted LEDs, and it's going to be equal to the slope times the voltage plus the intercept. So that's y equals the mx plus b. Intercept there we go. And then we have to do a conversion here also. Convert the predicted value to an integer. Convert. And so that's going to be int num LEDs to light, and then equal to static cast int, and then we're going to pass an argument predicted LEDs. Map the voltage level of the LEDs, int num LEDs to light equals, okay. So I think, no, static cast. Yeah, so we're good here, static cast. I think we're good here. Map the voltage, constrained. Oh, we gotta add, oh, no. So we gotta add in a constraint here. Constrain the value to be within the range of available LEDs. Okay. And then num LEDs to light, constrain num LEDs to light, 0 num LEDs. So 0 to max is what we're doing. And then we're going to do a clear on that. Yep. And I think the rest of this is pretty much the same. On the loop, let's see, clear. We're going to delete this because that's redundant now because we have the num LEDs to light. I don't think we have to do the mapping anymore on this. So we'll get rid of that. And then that clears that up. So we have num LEDs to light, constrain, num LEDs 0 to num LEDs max, which is 8. And then from there, we're going to light the LEDs with the for loop. Yep. And then we're going to do, that doesn't change. We're still to keep all that the same. And then this is all good here. Voltage, but we're going to say predicted this time because this is actually what we're printing out is the predicted LEDs lit. Predicted LEDs lit. And this is num LEDs to light. And this is all stays the same. Okay, so that's what we've done. So you can kind of compare. This is still our code that's running from before. I'm gonna close that, and then I'm gonna clear output, and then I'm gonna bring this down. Okay. Okay, so this is still running our old code from the last lab. And so this is not doing anything other than what it was doing before. What we've coded up here is not running in the lab yet. I'm sorry, what we've coded up here in the lab isn't running on the microcontroller yet. So we're gonna run it now. So let's compile it and see if we get any headaches here. We got a little bit of an issue. So float on line 20, predict, what is it complaining about? Slope was not declared. Okay, well, let's find out what that's all about. The slope was not declared. Slope. Oh, that's because we put, there we go. So I mislabeled that up there. So I said SLOP, that's supposed to be SLOPE. And let's rerun that. That's what the problem was. Okay. And we still got a, so then now fast, num lights constrain, LEDs 0 num. Oh, here we go. Missed a semicolon. Let's rerun this. Hopefully we didn't have any more issues. And I think maybe. All right. Okay, so that had a clean run. Now we're gonna upload the new one, and we're gonna upload new code, and then that should, it's going in. Okay, so that's loaded up. Okay, so now I've got. Okay, so now I'm running consistently 2 LEDs. I don't know if that's because we're running a little bit more we're generating more we're doing more computations. So our Arduino is no, it's just the conversion's a little different. So now it's tripping over at 1.2. Now this is predicted. So what this is doing is, this is saying, hey, independent of what's going on here, and independent of what we're doing here on the control system, I want you to take what's predicted, and rather, I want you to take the data, add that into the calculation on this voltage, this y equals the mx plus b for the linear regression, and then what I want you to do is give me a prediction on what it's going to do next. And so it's the forecast. And so it's predicting 2 LEDs. Where 2 LEDs are lit, and then it's predicting independently it's predicting 2 LEDs. So it's working as intended. Now this is a very, very, very simple machine learning model. It runs quick, it's simple, it's fast. Now when we get into something more complicated, and that's something that we'll tackle in MLAS 800, which is large language models and neural networks, that becomes a different animal altogether in that world. So we're just starting off with some of the basics, and then of course we talk through the supervised and unsupervised, and then this is something where this is supervised because we're using the voltage as training data to then feed to a algorithm, in this case a linear regression, to then predict what the next what's going to happen next. Okay, so as you look at what we're doing, what we've built, this all is working pretty good. I mean, we're as a model, looks like it's working pretty decent. Now, that's all we have. That's it. Congratulations, you got to the end of it. We're done with MLAS 700 for labs. Last thing we have this week is a lecture on development life cycles, and that'll be pretty much it. And then you have a learning reflection that's due. I did have a little tweak to the assignment. Instead of a 5-page, I'm kind of shortening it to a 3-page learning reflection, 3 to 4 page learning reflection. It's going to be due mid-December, December 15th, so I highly encourage you to go check out the assignment. It's been released, so you have plenty of time to look it over. You got 2 weekends to go through your prior learning reflections, the 2. Of course, if you have any missing learning reflections, please get those shored up. And then from there, you'll want to push that over and take that and add on to your learning reflection, your final learning reflection, and check out the assignment. There's more details there in terms of how to write that up. Okay, if you've got any questions, of course, I'm here. Feel free to text and or email. And with that, I will see you in the very final learning activity, which is going to be lecture 19. And take care.